Hi, in this video I'm going to discuss heaps in data structures and algorithms. Here's what you'll find in this presentation. What is a heap? Here we will define what is a heap and its property, and then the types of heap. So there are two types of heaps, max heap and min heap. And then we also have the heap operations. So some operations that we could use when dealing with heaps. So first, let us define what is a heap. A heap is a tree with some special properties. So the basic requirement of a heap is that the value of node must be greater than or 0, or it is a complete binary tree. So that means heap should form a complete binary tree as shown on the next slide. All heaps are complete binary trees. As you can see here, we have here the first node, and then we have to fill first the left subtree before going to right subtree. So we cannot consider a heap which is something like this. Let's say we have a root node, and then let's say we have a right subtree, since this is not a complete tree because we're missing a left subtree. Okay, so remember that in a complete binary tree, you could think of these nodes as a sequence of numbers wherein you read it from top to bottom, left to right. Okay, so 1, 2, 3, 4, 5. Now, if we remove this node here, let's say this right or left subtree, so we could only form 1 and 3. So we're missing 2. Okay, so there are two types of heap. We have the min heap and max heap. The min heap, the value of a node must be less than or equal to the values of its children. So meaning to say, class, we are dealing with the height of the tree. So the top node, or let's say the root node, is has the lowest value on a complete tree. In a min heap, the property of a min heap is that the parent node always have a lesser value than its child. Okay, and then the complete opposite of min heap is the max heap. The value of a node must be greater than or equal to the values of its children. Meaning to say, the parent node is always greater than its children. Okay? So let's have an example. We have here two complete trees, as you can see. The left complete tree or complete binary tree is a min heap. It follows the property of a min heap because all of its parent is lesser than the value of its child. Okay, so the value of the root node, or let's say this parent node here, is lesser than its child 2 and 3. Same goes for the left subtree. We have here the parent node 2, which has the value of 2, and it is lesser than its children. Okay, now for the max heap, all the parent node is always greater than its child. As you can see here, the root node is greater than its children 3 and 6. Same goes for the left subtree. We have here the node 3, which is greater than its children 1 and 2. Same goes for right subtree. We have here 6. It is greater than its children 4. So these are the properties of a min heap and max heap. You need to consider its height. Okay, so the higher the height of a tree, the lower its value. As you can see here, we have here the height of 0, height of 1, height of 2, height of 0, height of 1, and then height of 2. Okay, now let's try this. Suppose we have this complete tree. So this complete tree, we have to determine what type of heap is this. Okay, is this a min heap or max heap? The first thing you need to determine is a sample subtree. Let's say we have this portion of a tree. As you could see here, this is a max heap because the parent node is greater than its child. So this is a max. So this is a max heap. Okay. Now let's try the other subtrees. Now if I want to take this left subtree, as you can see here, this is a min heap since the parent node is lesser than its children. So this is a min heap. Okay. Now how about the other tree? Let's say this right subtree. So this is also a min heap because its parent node is lesser than its children. Now it violates the rule or the property of any of these two because this is a one complete binary tree. So if we're going to determine what type of heap this tree is, we cannot distinguish between the two if this is a max or this is a min because it is composed of a min heap and a max heap complete binary tree. So I mean to say it doesn't belong to any of those two types. Okay, so this is not a heap. This is not a heap at all. Okay. Now we have a process which is called the heapify. So this is a process of adjusting the location of a node in order to follow the heap property. So if we're dealing with a min heap property, meaning to say all parent nodes are lesser than its child. If you're dealing with max heap property, meaning to say all parent nodes is greater than its children. Okay? Let's say for example we have this complete binary tree. Okay? Now you have to determine by looking at its subtrees which one violates the property. Okay? So let's say for example in this part, this is a max heap. So this is a max heap. And then if we look into this, this is also a max heap. Okay. Now if we're going to look at this left subtree, part of the left subtree, this is a min heap. Okay. And also, how about this one? So this is a max heap because the parent is greater than its children. And then we also have this part. So this is also a max heap. So the majority of this complete tree is all of its subtree except for this one is a max heap. So meaning to say we could turn this into a max heap complete binary tree. So let's just remove this part. So it should be a max heap because this single node here is only violating the property of a heap. So we could use the heapify to move this node. So to heapify an element, we have to find the maximum of its children and swap it with the current element. Continue this process until the heap property is satisfied at every node. Now if we have here 1 as the one that violates the heap property of a max heap, we need to check its children, which one is greater than its value or which one has the highest value. Okay, so considering the child nodes of or the children of 1, we have 9 and 10. So which one of the two is greater than another? So we can say that 10 is greater than 9, so meaning to say we will swap 1 to 10. like this. And then we need to continue this process until we reach the part or the height of the tree we're in that 1 belongs to. Okay. Now again we have already swapped 10 and 1. Now let's move on to the next. So we need to check again the children of 1 or node 1, then see if which one of the two has the highest value. So considering 8 and 7, so we need to check which one of the two has a greater value or higher value. So since this 2 is 8 and 7, we obviously know that 8 is greater than 7. So we need to switch node 1 to node 8. Okay? So as you can see here, we have swapped this node 1 to node 8. And then, as you notice, we have already followed the heap or the max heap property by heapifying the node 1. Okay? Now, for the other operations of a heap, so we have the insert element, remove min or max element, and there are other several operations in heap, but this two is the most commonly used when dealing with heaps. Now, suppose we have to insert 19 on a complete binary tree. So since this is a complete binary tree, we need to follow the process of inserting an element while following its property or type. Okay? So since we're inserting 19 on a complete binary tree, it should start on the left subtree, not on the right. Okay? If this left subtree here points to a value, so that's the only time that we need to insert 19 on the right subtree. Okay? So we need to always check the left subtree. Now, if we put 19 here, we need to swap it to 14 because we need to follow the property of a max heap. Okay, so as you can see here, 14 is now at the third level. Okay, so 0, 1, 2, and 3. Third level or third height, okay, of the tree. Now again, since we need to follow the max heap property, so as you can see here, 19 is a child of 16, so we need to swap them again. And then let's see if the parent node of 19 is lesser than 19. Okay, so since 19 is lesser than 31, so we don't have to swap it on its parent, which is 31. And that's it. We have followed the max heap property on this complete binary tree. Again, we have another one. We have the delete, okay, min or max element. So when we say delete max, meaning to say we are just deleting the root. So you cannot choose which parent node or which node to delete. It always delete the highest value or the lowest value, which is the root. Okay, so when that happens, let's delete the max. So we have to find the deepest node, which is 14, and then swap it or replace or place it on the top of the tree. Okay, so this is the deepest node. Okay, and then after doing that, we need to use heapify in order to rearrange this to follow the max heap property. So here in this complete binary tree, we need to form a max heap. So we switched 14 to 19, and then again heapify it again. Okay, so that's it. We swap 14 to 16, and then that's it. We have already followed the property of a max heap. And that's all for now, class. Thank you for listening.